I just want to beat this up a little bit more for you. It's very important that we understand the longitudinal cables, and of course the transverse cables also. D1, D2, D3, D4, D5, and D6. Reminds me of a joke. Center line of this structure is right here where the drain pipe is. The span between D1, the two D1s, this is D1 on this side also, and this is D1, is center lines 1 foot 10 and 1 foot 10. That's what, 2 foot 8 inch, 3 foot 8 inches on center line. That the loads had to transfer. That this transverse cable, that transverse, that's the cable going across here, transfers the loads to the longitudinal cables. Where it was most concentrated, it had to transfer 3 foot. One of the most concentrated locations, 3 foot. What did I say? 3 foot 10, 110, 3 foot 8 inches. And D1, I'll zoom that in again. D1 has, this is the tendon of the deck, tendons on the deck. This is D1, was 100. You see the distance are down to D6. They're all the same length. So this shows you what's going on there. D1 has 12 tendons. So that one has 12 tendons, not 19 like the rest. It also had a force that was a stressing force tendon kips 527, and the dead end would be so here we go, and it was going to be, where we go here, after anchor set. So they were going to elongate 14.23, and after anchor set it should be this much. So they do measurements, and it should come to that. Tendon profile 12, up station 2. Let's slide over. So no change in this down through 6. Yet our kips are a lot. Here are the kips on these guys, 1 through 6, 745, 745, 7, all the same. 835s, 835s. This D1 I find just amazing that it's a different profile altogether. 12 tendons. Here we are, and much lower kips. Now, I'm not done with that, because we're going to look at, let me do one more thing. Let me slide. Oh, okay, I'm in there. Let's slide that down. So this is the one D1 that has the least amount of kips applied to it, and that's the clamp force. These all have equal clamp force on it. This has less, and it's a smaller bundle. Also, the diaphragm, its trumpet area, its reinforcement is different also to the rest of them. Now going to this is the structure over here in this diagram. This is the 2017 plans of it. Of course, we don't have the as-built, so we're going from here. This is 2, that's 11. As you read it, and I talked about it before over here too, that they were supposed to not move this structure. Oh, that was awesome. Awesome fail. Awesome fail. Give me a second here. And perhaps I need to pause it while I get that. Let me do that. I don't want to edit this, so let me just do this. Bear with me. Okay, so I'm back. Now, if you look down here, erection of main span, the bottom left-hand corner here, install bearing pads at Pier 1 and shim plate at the pylon base. Well, that was supposed to be done. We talked about that. Also, the vertical post-tension bars were supposed to be secured, which would secure the bridge from. It could have helped with part of the diaphragm and it not having a negative load on the back end. It could have helped it from pulling off the pedestal, off the pier. Grout span between precast section, diaphragm, and pylon base. Well, that was supposed to be done so it can transfer the loads equally down the diaphragm, the bottom of that area here where it connects to the pier, rest on top of the pier. Stress pylon vertical post tension bars. Those are those guys there. I have a longer video I'm showing that, but this video I decided to jump on real quickly and give it to you today, just now. So now we slip over to this one, and let's wrap this up a little bit. After concrete compression stress has reached 6,000 psi, stress post tension of the main span in the following sequence. So this is the pre-stress. I'm sorry. This is the initial stress, and it says stress deck longitudinal tendons D1. If you guys recall, D1 is right here. This guy. This is D1. Give you another shot of it. This is D1. And then this is D1. So when they say D1, it would be left, right, right, left, however they decided, or both together at the same time. Stress longitudinal tendons D1. Then what they jump to next is stress canopy longitudinal tendons C2. So stress deck longitudinal tendons D1. And then 2, go to the canopy and stress C2. Canopy's above D2, C2, it gets stressed. So you went from D1 to C2 on the deck, kind of like a diagonal, if you will. All right, on both sides of that. And then it jumps back down to, as you look to the left here, stress post-tension bars and diagonal members 2 and 11. So now they did these guys, 2 and 11. So we've got 2 on the base, 2 on the canopy. So 2 on the deck, 2 on the canopy. Now we got 2 and 11. Now this is where the problem starts. Because then after they did that, think about this. After they did that, this, when it now puts stress under stress deck longitudinal tendons in the following sequence, D2, 3, 4, 5, and 6. So then they went to D2 and then D2, D3 and then D3, D4 and D4, D5, D5, D6, and D6. The problem is when they were stressing D2 through D6 and into the canopy, the last 2 pieces in the canopy, 3 were in the 2 in the canopy, 4 all together, so they had to go back up there one more time. When they did that, the loads were already deducted. Imagine I'm doing my own, taking liberty now to help you understand it. The loads of the structure were deducted when you did 2 and 11, because right here, stress post-tension bars and diagonals numbers 2 and 11. Once they did that, once you jumped down to doing 2, 3, 4, 5, and 6 of the deck, well, it arrived at a clamp force much sooner than it would had D2 and D11 not been already post-tensioned. It arrived at a clamp force faster. So that numbers we see down here of 745 was arrived at faster because it did not have the stress of D2 and D11. Whatever D2 and D11 took off of this bridge, the stresses they removed off the bridge, they were put back on once they detensioned it after the move. When they moved the bridge, they put the bridge in place. Everything was great right then as they started taking everything apart. And as you recall, one of the videos I posted showing that the MCM, I believe the representative was saying, we just have to detension 2 and 11. Problem was they were never supposed to detension 2 and 11 as the plan stayed, not until the completion of the bridge. And I did a total big video on that. If you detention 2 and 11 at that point, whatever loads that 2 and 11 were taken care of, they're now applied to the bottom canopy, and the decking, and the canopy. And those loads were obviously hugely significant because they caused the cracking, the failure of the elongation of these tendons, because they have a new force on them. That elongation brought them to, well, it would be number 1 and 2 for sure on the one side of the deck. Experience it showed on the one side of the deck we see it has larger cracking than on the other side, and then looks like it transferred over. So the elongation was experienced more on D1 over here, D1 and D2, and then it worked its way over, I believe. But that's because they released those forces off 2 and 11, elongating these to the point where they no longer can hold they no longer can perform. You just can't. In essence, you had 2 here and 2 here. specifically down on this end, the station, you had the forces, the way this is designed, um, experience more force on this end of the structure than that end of the structure because of the design, the spacing, the non-equilibrium design made it so that it still wanted to transfer the forces to the lower deck and also from the canopy, trying to get it over here too. Yeah, I know about zero force members. Okay, so just you know, don't troll yourself. So now this span, it could not make it out here, but 2 and 11 will remove the forces, and the forces trying to make themselves still over, always over to some support. The deflection was too great right here, and ultimately the ultimate weight, dead load of the structure, um, sheared off here, and the cracking shear showed, creating a bending moment. Well, here and here is where the canopy cracked, and here is where it decelerated down to zero, as we know with the video, um, with the video content online. In a minute. And as we see, to prove my point, after that everything was the transverse cables were done right here. Stress, bottom slab, transverse, post tensioning, alternating, end stresses is required for the transverse tendings. So you would opposite sides, one to other side of the deck, this side of the deck, doing these transverse cables, which are coming across this way. So do this one and do the other side. Do this one and do the other side. Left and right, alternating. As we come next, after they've completed that task, they then went to the uprest of the truss members, 3 and 10. See the opposite the symmetry, 3 and 10, 5 and 8, 6 and 7. And these don't have 4 does not have any member in it at all, and now there's 9. So 4 and 9 do not. They're just compressive. As to extrapolation, they're compressive. Now, so this is all I'm driving at. All I'm driving at is when they removed 2 and 11, whatever forces that 2 and 11 were taken care of before they tensioned the bottom deck, they then put back on after the fact. And when they did that, it just released onto this deck, and there we go. That's our longitudinal cable failure. For simplest reasons, this doesn't make sense though, because it was not supposed to be removed until 2 and 11 was not supposed to be detensioned until the end, till everything was completed. That's what I find just craziness. Also, the temporary supports were supposed to shall remain in the middle of the cross section during They were not. They did not remain. They did not remain. They used the chains, and I said it. I extrapolated through another video with you guys that the chains would put a force out here that they should not have used chains at all. If they predict a failure, that the chain needs to hold some part of the deck up, well, then they're transferring loads where they were never designed to be transferred, not to the underside of the canopy pulling down, and for surely not on the outside of the transverse cables. I just find that just, what are you doing there? Yeah, we talked about that. There was one more point I wanted to show you. Oh, sorry. Here we go. That's the backspan. I wanted to show you that the backspan is very amazing. I got to pause the video and get it for you. So you just want to see if it's up here by 2 or 3 screens. And no, I'm going to pause it and I'm going to grab something for you that's going to be very telling of design. We have one more page to click through, but here's the backspan rather. And you see the tendons are the same. And the length, to verify for you guys, D7, D8, D9, it's only 3 tendons in the lower deck. 98, and you see the length, and you see the kips all balanced, and you also see that the elongation will all be the same. And scrolling over, again, you see the elongation is the same on this one, on D1, but yet it's not, so its ultimate kips are a lot less, being that it has less tendons. Let's go to something else, which is counterintuitive, right? Hold on. So take note, this is the backspan, D7, 8, and 9. Center line is here. Take note, 7, 8, 9, the profile is straight. And this is what I'll end the video with. Here's the backspan. Look at the center line of the structure now, and here's D7, 8, and 9, and then we go opposite, D7, D8, and D9. Wow, I can't help but want to tell this joke. And look at the, before you get D7, it's 4 foot 8 inches span off of there. Now it's only 100 foot long. The other one's 175. But if we do some extrapolation here, and well, this is the 100-foot bridge, you would think the loads would want to transfer more. The spacing would be, the width of the bridge is still the same, but yet they calculated that 4 foot 8, so practically 10 foot in span between here and here, unsupported span on the transverse cables between each other. And then the span that it would cross, the transverse cables would cross unsupported span would be, well, let's be a little more accurate, 16 inches. So that's 9 foot 4 inches center line of each one of these. So from here, from D7 to D7, 9 foot and some change. 9 foot, what did I just say? 9 foot 4 inches. That's the center line of the structure where all the canopy transferring the loads, theoretically transferring the loads, as everyone who thinks this is a typical truss bridge, would transferring it to the transverse cables and making it out there. So you can see where somebody like Denny Pate, if he thinks this would work, then that little bit of cracking there would be like, you know what? I've got some redundancy in this. I'm not worried about it. Perhaps that thinking got him in trouble. This is major. So imagine the forces of that truss on these transverse cables, and the spacing is the same. All right, I just wanted to show you that. So you can do some extrapolation on this yourself that realize, wow, look at the span, that they actually thought that the transverse cables are the ones going to transfer all the loads to the longitudinal cables. And look what the greatness of span that it could do. Wow, amazing. So what I'm driving at is, if this is 100 foot in this work and design by all these multiple engineers passing it, then the 175 foot, the extra 75 feet, gave us the other 3 closer inbound. And specifically my D1 that I'm so irritated about with this issue with being, why does it have to be even less? Why? Why make it less? That's just, it's an insult to injury. I'm going to do a video for you guys. I'm wrapping it up, but I want to give you something visual. Imagine you guys holding books, a set of books, 10 books in your hand, and press your hands together. Now lift the books up. You can imagine the clamp force that's required to hold those books in the air. Now, imagine now you had, I don't want to bug you out psychologically, but 6 fingers as a bridge would have, but we can go with 5. Now, instead of applying the clamp force with the palm of your hand, now apply it with your fingertips. And that's going to be your clamp force that you're going to hold the books in the air with. Now remove your index finger from that clamp force system, and now you see that your system is now being loaded by the other 4 fingers, or thumb and 3 fingers, however you guys like to think of your hand. So your clamp forces are being reduced or being made less. Well, that's the same thing as doing D1 right here with the least or less of right here, D1. If these are all equal, but you on this finger, you said, I just only wanted to have so much clamp force. It's an imbalance. You can see that, and I don't get if they're all the cables. He saved that much money because this has less cabling in it than the rest. I just find that just wow. You're talking about skimping on budget. This has got to stop. I'm hanging up here because I don't want to get too dramatic. Thank you for watching, and please subscribe.